Welcome to day 5 of our unit on exponential functions and logarithms. Today we're going to learn about properties of logs. So let's just hop right in here with some examples. We're going to evaluate these expressions. So let's see what we got here. 3 to what power equals 1/9? We know that's -2. And 3 to what power is 243? That's 5. So that gives us 3. All right. What about B? That'll be 2 plus 1, which is also 3. And this will be 0 plus 3, also equals 3. So it says, what pattern seems to hold here? I'm going to hold off on answering that question because I think the pattern you're going to say is, oh, everything equals 3. But that's not really the one we're looking for. So let's go ahead and do some more. So all these were addition. Okay, keep that in your mind. All these are subtraction that are going to be next. Let's do all these and then we'll see if we can pick out a pattern. All right, let's see what we got here on D. 2 to what power? That's going to be 6, right? 2 to the 6th power, 64, and that'll be 3. Oh, there's another 3, but I promise you guys that's not the pattern we're looking for, that everything equals 3. This will be 5, and this will be 2. So that's 3. This will be 4, and this will be 1. So that's 3. Okay, so we're going to roll on. But again, as we're thinking about a pattern, just remember the first 3 were addition. Second set of 3 are subtraction. And this one is even harder to see the pattern. So I'll actually tell you this pattern when we get to the end. So let's see, 10 to what power is 1,000? Shocking, it's 3. That's 3. This is 3. Let's scroll back up here and see if I can help you here, because I think it might be hard to figure this out. You can pause right now and think about it if you want to. But what about this? What if I said the log base 3, what if I multiplied these two numbers, 1/9 times 243? What is 1/9 times 243? That is 27. So log base 3 of 27. Oh, so the log base 3 of 27 is equivalent to this. What if we did the same thing here? What if we multiplied the 9 and the 3? Log base 3 of 9 times 3, that would also be the log base 3 of 27, which would also be 3. And what if we did the same here? The log base 3 of 1 times 27, also 3. So, what we found out is if we multiply these two numbers and take the log base 3 of that product, then that does equal the sum of the logs. So now let's see what we can come up with our pattern for subtraction. I would like you to stop here and see if you can figure out what the pattern is here. All right, anybody get it? Is it this? If I take the log base 2 and if I divide these two numbers, 64 divided by 8, that gives me the log base 2 of 8, which is 3. If I divide 32 by 4, I get the log base 2 of 8, which is 3. And the same thing holds true here. The log base 2 of 16 divided by 2 is equal to the log base 2 of 16 minus the log base 2 of 2. So our patterns that we see here, is the sum of the logs is equal to the log of the product, right? That's what we saw. And the difference of the logs is equal to the log of the quotient. All right, so that's what we discovered. This one here is a little bit different. This is actually pertaining to exponents. So what I have going on here is that this is the log, and of course it's base 10 of 10 cubed, right? That equals 3 times the log of 10. Okay, let's look at h. If I do the log base 2 of 2 cubed, I can bring that 3 out front, and that'll be 3 times the log base 2 of 2. So what happens is when you have an exponent, like here, log base 5 of 5 cubed, you can bring the exponent out in front and evaluate it that way. That equals 3 times the log base 5 of 5, and in all cases they do equal 3. All right, so now, knowing what we know there, let's try to write 3 different expressions using each rule once that are equivalent to the log of 36. Okay, so we're going to use our sum of the logs equals the log of the product. So how about this? How about the log of 36 equals the log of 6 plus the log of 6? Is that going to work for us? Or, well, we don't have to pick 6 and 6. You could do the log of 9 plus the log of 4. Any 2 factors that multiply to give me 36. Okay, let's do a quotient now. Log 36, how about this? Equals the log of 72 minus the log of 2. That'll work, won't it? And how about this? The log of 36 equals the log of 6 squared. So that would be 2 times the log of 6. And if you don't believe it, guys, punch those numbers into your calculator and you'll see that those rules do indeed hold true. And here they are in a little box, the properties of logarithms. A, B, and the base B are all positive numbers, but B can't be equal to 1. So you've got the product property that we went through with our first 3 problems. The sum of the logs equals the log of the product. Quotient property, the difference of the logs equals the log of the quotient. And the power property says that if you have an exponent up here, that you can just bring it out front and multiply that by the log base B of A without the exponent. All right, so a proof. You thought you were done with proofs. This is not hard, though. We're not going to do, statements and reasons and all that stuff, though. What we're going to have to recall is the change of base formula. Change of base formula, which you remember if you have the log base B of A, that equals the log of A over the log of the little b, right? We just make the base the same. So let's put that to work here. So let's see what's going to happen on our left side here. We're going to operate on that first. So if we apply the change of base rule on both sides here, what we're going to have on the left side is the log of AB over the log of B, the little b, and I'm just applying the change of base formula, and I'm going to apply it on the right side as well. So the first term here will be the log of A over the log of B plus the log of big B over the log of little b. Okay, all I did there is apply the change of base formula across the board to those 3 terms. Okay, so now what I have is an equation with a common denominator, right? The denominator is the log of b all the way across. So I've proven what I need to prove, and that is that the log of AB, because if the denominators are all equal, then the numerators have to all be equal. The log of AB equals the log of A plus the log of B, and this would be true for any base. In our case, we're talking about base B, but for any base. We'll say any base B, okay? So that was just a very simple matter to prove that. Okay, so let's do some expansion here. I'll do 2 or 3 of these, and then I want you to pause and you do a few. So we'll do those, and then we have some condensing and quite a few examples here. So you'll probably want to pause and do some of these by yourself, and then so you don't have to listen to this whole video here. So let's expand by using our properties there. So what do we know? We know that this is going to be log base 3 of 9 plus log base 3 of x. That's our first property we learned, right? The log of the product is the sum of the logs. Oh, I can simplify this though. Sorry, that's my Google Nest talking to me. She thinks I'm talking to her. Log I had to go turn her off. All right, log base 3 of 9 is 2. So it says expand and simplify when possible. So we got to change that to 2. 2 plus log base 3 of x. All right, what are we going to have here? Let's see, we're going to have the log base 3 of 8 plus the log base 3 of x cubed, but we're not quite finished, right? Because we've got that exponent up there. So we got to take care of that. Log base 3 of 8 plus 3 times the log base 3 of x. We're working with these properties. They'll become second nature to you in no time. All right, this is a quotient, so we know it's going to be a difference of 2 logs. So we got the log base 2 of 3y squared minus the log base 2 of 4. All right, now we got to divide the first one, the 3y squared, even further. So we've got the log base 2 of 3 plus, and I'm going to go ahead and bring my 2 out front, 2 times the log base 2 of y, and then the log base 2 of 4 is just 2, of course. All right, why don't you pause here and try to do these two, and then when you come back, I'll have them worked out for you. All right, here's what I got. E is kind of a doozy, so please do check me out here. Make sure I haven't made an error, which is very possible. It's about midnight right now. Okay, but I know I got to use in D, I got to use the product rule and the exponent rule. So hopefully I captured all that. There's everything in E, but the first thing I do is I move my 2 out front. That's what happened right here. And then I just start dividing all those things up. And you see my final answer. This is a 2, not a Z. Log base B of 2 right here. All right, so check me out, see if I got it right, and of course, you check your answers with each other and let me know if I've made an error somewhere. Okay, now we're going to condense. We're going to put it back together and also simplify when we can. So we've got a sum, so we know that's going to turn into the product. So what we got here is the log, come on, log base 5 of 7 t cubed, right? Because the 3's got to go up here, and then I got to multiply those two, take the log base 5 of it. Okay, I'm going to do this in a couple of steps here. So this will be the natural log of the square root of 3. I'm going to, when I put the 1/2 up there, I'm going to change it to the square root of 3. And this is minus the natural log of 27 to the 1/3. Cube root of 27 is just 3, so I'm going to go ahead and simplify that now. And then I've got the plus 2. All right, so I know that this first part is going to be a quotient, so I'm going to have the natural log of square root of 3 over 3 plus 2. Okay, all right. Why don't you, I think you can do these next three, C, D, and E. So go ahead and pause here again, and then I'll put the solutions up for you. Okay, let's see how we did. I'm not going to talk through all of these, but please just look at the answers I got. As always, you know, there's a chance I've made an error. If I have, please correct your paper and please make a note of it so that you can help me correct my paper when I get back. But I've applied the properties as best I could and didn't write out every single step, but wrote a lot of the steps. So check over those, see if we agree. If we don't, we'll discuss it when I get back. All right, moving on. Now these are fun. These are like a puzzle. So some of you guys are gonna like these a lot. Some of you not gonna like them at all. Let's see how we do. I'll do the first one, and then you'll pause and you'll do the second one. So let's see what we got here. This is going to be log base b of 60 minus log base b of 49. Okay, so now if log base b of 2 equals a and log base b of 3 equals b and so forth, as you see there in the instructions, we are to write all of this in terms of a, b, c, and d. So here's the way I'm going to think about this. This is the log base b. What of those factors up there can I use to get 60? Well, let's see. I can do 2 times 2 times 3. Let's see. That's 6 times 2, 12 times 5, right? That's 60. 15 times 4, yep, that's 60. And this is minus log base b of 7 times 7. All right. So now what I got to do is I got to expand all this, right? Because I've got the log of some products, and I know that equals the sum of the logs. And then I'm going to have a quotient too, because there's a negative in there. So let's see what we're going to do here. Got the log base b of 2 plus the log base b of 2. There's my second 2, plus the log base b of 3 plus the log base b of 5. And then I've got minus the log base b of 7 plus the log base b of 7. Actually, I take that back. I'm not going to use a quotient. I'm not trying to condense this. I'm trying to get it in terms of A, B, C, and D. So let's see what I've got here. Log base b of 2 equals A, and I've got 2 of those. So that's going to give me 2A. Log base b of 3 is B. So that's going to be plus B. Log base b of 5 is C. And minus, let's see, I've got 2 log base b of 7, so that's minus 2d. All right, I told you it was fun. Okay, so you see how I did it. I want you to pause here and do b and then come back and check your answer. Okay, let's see how we did. First, I divided up the quotient into a difference of the logs, and then I divided this up into the sum of the logs because it was a product, then applied my exponent rules and all these rules, and in the end, you see I got 2b plus a half d minus 3a minus c. And you got to remember here, guys, this negative sign, it's got to apply to this and to this. That's why that last sign became negative, in case you're wondering about that. Okay, that's fun. Here's something else that's fun. You're going to love this last part. Okay, so we're going back, change of base formula again. Okay, so you remember that when I have the log base b of a, that equals the log of a over the log of b. We've done this many times already. And we know that's also, we could use the natural log of a over the natural log of b. As long as we have the same base, it's okay. All right, so we can see then that the log base b of a over b does not equal the log base b of a divided by the log base b of b. And right, we knew that because we just learned that that equals the difference of the logs. Okay, but anyway, now we're going to use these two things together. We're going to use the change of base formula and some of the properties of logs to do some other fun kind of puzzles. Okay, so for example, let's remember this. If we want to rewrite the log base 3 of 7 using the change of base, we just say that's the log of 7 over the log of 3, or we can use the natural log of 7 over the natural log of 3. All right, so that's all we're trying to remember. So now for A and B here, let's determine whether each statement is true or false. You know we love a good true or false statement. All right, so let's use the change of base formula. So on the left, we're going to have the log of 49 over the log 25. And on the right, we're going to have the log of 7 over the log of 5. Well, they don't look the same, do they? But what else could we do to the left side? I think somebody's probably got an idea. What if we did this? What if we said this is the log of 7 squared, and the denominator is the log of 5 squared, and the right side's not going to change. We can't really do anything to it. And now if I apply my exponent property to the left side, I've run out of room here, so let me bring this over here. That ends up being 2 times the log of 7 divided by 2 times the log of 5. And my 2's will cancel out, right? So the log of 49, the log base 25 of 49 does equal the log of 7 over the log of 5. So that's true. True. Okay, what about this one? Let's see here. If we apply our change of base formula, we'll have the log of A over the log of B. That's still all raised to the n power. Let's see what we got on the right. We have n times the log of A over the log of B. So those two things clearly are not the same, right? I mean, I guess they could be if n equals 1, but n doesn't always equal 1. So we're going to call that one false. Now, number 9 here, number 9 is a true stinker. So I'm going to leave you with it. I'll write the solution up here, but please, you have to pause and try to do this one yourself. It is really a brain teaser. So stop, try to do it, come back and check your answer. All right, here it is. I told you it was a doozy. So the first thing you want to do is use the change of base formula on both your denominators. So the first denominator will be log 4 over log 5. the second denominator will be log 8 over log 7. Okay? Then what we got to do is those are both complex fractions now, so we have to change them so that they're not complex fractions, and that's by multiplying top and bottom by the reciprocal of both of the denominators. All right, and that gets us to this step. Okay, then what I did is I changed, you see on the denominator now I have log of 4 and log of 8. I can change both of those to base 2 because 4 is 2 squared and 8 is 2 cubed. And then when I apply my exponent rule, that gets me to here. So I have 2 times the log of 2 and 3 times the log of 2 for my new denominators now. And then I can cancel the 4 and the 2 here, leaving me a 2 up here, the 3 and the 3 here. And then once you get to that point, it goes kind of easy because now you got a common denominator. So you can combine those two fractions. And then once you get them combined, you can start applying your exponent properties again. So the 2 can come up here, make that 5 squared. So that's the log of 25. And then you can remember that the sum of the logs is the log of the product. So 25 times 7 gives me 175. And then I use the change of base formula in reverse to rewrite the log of 175 over the log of 2 as the log base 2 of 175. So if that wasn't fun, I don't know what is. And that's it for today. I'll see you next time.